SwayamPrabha. Digital India. Educated India.
Welcome back to the discussion sessions. So, I will remind you that we were discussing in our last session the composite materials and the classification of the composite materials, and we said that we have the laminar or layer composites, okay. Then we have the particulate composites, all right. Particulate composites are the discrete particles of one material surrounded by matrix, and the common examples we said that this is the concrete, hard particles and the soft matrix, this is the property. Pronounced strengthening, better creep resistance and the toughness. Examples are the cemented carbides that are used as tools, tungsten carbide, tantalum carbide or titanium carbide dispersed in the metal matrix, and that metal matrix, as I said, that generally the cobalt is used for that kind of a metal matrix in the composite. They make the very hard stiff carbides can withstand high cutting temperatures, but they are extremely brittle, okay, cannot withstand the shock load, as I said. Toughness imparted by the cobalt matrix. Okay. Now, I also discussed this in the last session that those properties depend on the size of the particles, volume fraction of particles and the mechanical properties of the particles and the matrix. And also I mentioned the mechanical properties of the composite may not be the same as the properties of the particles and the matrix, like in case of a solution. Now, next is the fiber composites. Fiber composites are most popular composites. Matrix provides ductility and the toughness. Fiber carries the load. So, we have in the fiber composites there are fibers, okay, different kind of fibers of different materials, we are coming to that, and the matrix of different materials. Now, those matrix, that matrix provides the ductility and the toughness particularly, and the load is carried by the fibers. Graphite and Kevlar most popular fibers. Fibers are made of graphite and the Kevlar. Kevlar is the low density, almost half of the aluminum, okay. High ultimate tensile strength, this is 4 to 5 times that of the steel, that is very important, or the aluminum. Okay. So, tensile strength, as you understand that this is ultimate tensile strength particularly, this is important for the engineering materials, and when it is more than steel, 4 to 5 times steel, it is very important. So, therefore, those kind of composites are used in our field of mechanical as tools, for also for machining. For example, glass fibers most widely used in the polymers. Okay. So, here we have the fibers as the graphite and the Kevlar, but the glass fibers they are used in the polymers. Okay. Silicon carbide and aluminum oxide, they are the main fiber materials for the ceramics, by the way. Polymeric matrix used for the low temperature, that is for the 300 degree centigrade, when it is the polymeric matrix, because otherwise they will melt, you understand that. But the metal matrix also used for the high temperature application, when the temperature goes beyond 500 600 degree centigrade. There, of course, the polymeric matrix cannot be used because they have low melting temperature, melting point. Examples are the steel reinforced concrete, that is the concrete where we have the steel rods in between. Okay. Nylon reinforced tires. So, automobile tires, for example, you can see that they have the nylons and they have the very thin metallic wires, okay, they are reinforced. Glass fiber reinforced plastics for car bodies, furnitures, okay. So, that those are the glass fiber, and boron reinforced aluminum composites for aircraft and the rocket components. Okay. Here, as you understand that we need the high temperature resistance. So, there the boron reinforced aluminum composites are used. Sporting equipment such as tennis rackets, right, skis, fishing rods, they need to have the high strength. Okay. Fishing rods need to have the fatigue resistance, bending, they bend a lot. So, they cannot have the the brittleness and so on. Properties depend on properties of the fibers, volume fraction of fibers, aspect ratio of fibers, orientation of fibers, in which way it is oriented. So, initially we discussed, if you remember, that the strength and the required properties are obtained by different orientations of this fiber, all right. So, therefore, we are saying that properties depend on the orientation of fibers, degree of bonding between matrix and fibers, how well they are bound, okay. Properties of matrix. So, properties of fibers, properties of matrix, of course, and how the volume fraction is made, what is the aspect ratio of the fibers, okay, orientation and so on. Now, let us see the properties of those materials, all those materials that we have discussed so far. So, they should have certain properties that we will see, okay. Physical, mechanical or chemical. The properties can be subcategorized as the physical property, mechanical property or chemical property that you know. So, in the physical property we have the properties like density, thermal conductivity, electrical conductivity. Okay. In mechanical properties we have the material response to the applied load, bending for example, okay, stress, strain and so on. Chemical properties, corrosion for example. So, many others which we will look into details from now on. Let us see. Ductility. So, mainly those properties we will discuss here which are important in the field of engineering, particularly in the field of mechanical engineering. When we are designing the part, when you are using the material for the tools and so on. So, those properties that are required and that are most popularly used in case of design and manufacturing, those properties we will be discussing. Ductility. Ductility is the ability of a material to be deformed plastically without fracture. So, this I have shown it to you in the stress strain curve, that it can actually go beyond the yielding point. Okay, you remember, those are the ductile materials like mild steel for example, whereas the cast iron as the brittle material cannot go beyond that point, beyond the elastic range. Okay. It cannot have the plastic deformation. So, those materials which have the ability to be deformed plastically without being fractured, they are the ductile materials. So, the ductility is defined by that. Elongation up to the point of necking, that is the uniform elongation, is taken as a measure of ductility. How it is measured? This is how much it has been elongated up to that necking point. Okay. Necking point I am talking about when the material is tested. You remember, there is a ultimate tensile stress when you are testing, when you are measuring. There you are actually pulling on two sides that specimen, and after some time there is a localized deformation, and that localized deformation is the necking. So, that elongation up to the point of necking, and where it is uniform elongation, of course, this is the measure of the ductility. Useful in metal forming operation. We have to have the metal, ductile metal for the forming operation, otherwise it will break, right. Not only it will break, what will happen is that in the case of hot forming for example, okay. There we heat up the material so that the ductility becomes more, so that it can be easily formed, all right. So, therefore, we are saying that this ductility property is useful in the metal forming operation particularly. Brittleness. Brittleness is opposite to ductility, in the sense that those materials which will be ductile materials, they will not have the brittleness, and vice versa. Brittle materials are not ductile materials. Let us say not have the ductility, that means the cast iron, for example, you cannot have the plastic deformation, as I said. So, they are brittle material. Fracture and yield points similar, okay, because they cannot go beyond that, they fracture actually. Indicates lack of significant plasticity, but not strength. Strength is high, but lack of plasticity. They cannot go beyond this yield point, it fractures. Yield strength can be very high. This is one good property of those brittle materials, that although they will not have the elasticity, or sorry, they will not have the ductility, but they will have a very high yield strength. For that, those materials are also used in those particular fields where the high yield strength is required. Okay. Toughness. Toughness is the ability of a material to absorb energy in the plastic range without fracturing, in the plastic range. So, this is the absorbing energy, means that it will actually withstand those kind of shocks, for example. So, sustains shock loading. So, this shock loading, it will absorb that energy and it will not break, it will not fracture. Area under the stress strain curve is a measure of toughness. Okay. So, stress strain curve I have already shown it to you in one of the slides. So, it is a stress, it is a strain. So, let us say if it is ductile material, so it will be something like this, okay, if this is the stress. So, this area under this load, under this curve, this is actually the measure of the toughness. Okay. Desired in parts such as railways track, train coupling, gears, crane hooks, cutting tools. Okay. Now, there in all these rail, when the rail moves at a very high speed, it will have the shock loads, the fluctuation in the force, okay, fluctuation in the load which is imparted on that. Train coupling similarly, gears, they will have a tremendous shock loading when it is entering to gear, two teeth are entering or disengaging. Crane hooks, all right, cutting tools and so on. So, there the toughness property is very much required. Hardness is the resistance to indentation. You cannot make any indentation, okay, you cannot make a hole very easily or indentation on the material, and then we say that that has a very high hardness, all right. Now, normally those materials which are brittle materials, they are also very hard materials normally. In general, implies resistance to plastic deformation. That means, this hardness is overall, you can say that plastic deformation, when it resists, though then it is more hard, it is harder. High hardness implies higher yield strength. Okay. So, if you remember, I will go back to that yield strength can be very high for brittle materials, you can see from this slide. So, cast iron is an example I gave you while I was speaking about the cast iron, that it is very brittle, but the yield strength will be very high. So, here that is what we are saying, this high hardness implies higher yield strength. Two popular scales to measure the hardness, Rockwell scale, Brinell scale. Okay. New Rado watch, for example, of this VHN 10,000, they can only be scratched by high purity diamond. Okay. This is an example that this watch cannot be actually scratched. This is a scratch proof material. All right. So, there the hardness has to be very high. Used in cutting tools, materials with high hardness with these properties, they are suitable for making the cutting tools. stiffness. All right. Stiffness is the extent to which an object resists deformation in response to an applied force. The complementary concept of flexibility is pliability. Okay. The more flexible an object, the less stiff it is. So, you can understand from this what is the stiffness. That means, overall when the load is applied, okay, the deformation will be less. So, those materials we call, in one word, it is a stiff material, meaning that when it is not bending, less bending, so that means it is a stiffer material. Okay, that is how we can call it. Stiffness is how a component resists elastic deformation when a load is applied. Elastic deformation is in the beginning. Okay. So, in this curve, this is the elastic deformation, and after that it is the plastic deformation. All right. So, what we are saying is that a component resists elastic deformation when a load is applied. Hardness is resistance to localized surface deformation. See, there is a very little, why I have written down this, to show you that there is a very little difference between the stiffness and the hardness, and you have to really distinguish the hardness from the stiffness. Once again, the stiffness is a component resistance to the elastic deformation when a load is applied. Hardness is the localized surface deformation resistance. Okay. When the material or the part is resisting to the localized surface deformation, then it is the hardness. So, hardness and stiffness, they are not the same. In some places I have seen, in fact, some students, they actually confuse the hardness and the stiffness. Okay. So, this is not to be confused. Say this is the stress strain curve, this is the along the y axis we have the stress, along the x axis we have the strain. This is the stress strain curve, this shows the relationship between the stiffness and the yield strength. Okay. See, this is the yield point. Okay. After that the plastic deformation starts. All right. Here this is the elastic region. So, if you remember, in the stiffness is the extent to which an object resists deformation in response to an applied force. Okay. This is the elastic deformation when a load is applied, how the component resists, this is the stiffness. So, that is what we said, that here the slope in the elastic region is the stiffness. Okay. And beyond that yield point is the plastic region, and here the slope is the stiffness. All right. This slope is the stiffness here, this is the non-elastic region, and here it can actually fail. So, yield point is here, all right, as you can see here. Now, the strength measures how much stress can be applied to an element before it deforms permanently or fractures. This is the strength of material. When we say, that means it is the measurement of how this stress can be applied before it deforms permanently. Okay. Stiffness is an indicator of the tendency of an element to return to its original form after being subjected to a force. Okay. Because it is in here. So, how much it is subjected to, I mean how much it can come back to this, all right, that is the indicator of the tendency of an element to return to its original form after being subjected to a force. All right. Hardness measures a material's resistance to surface deformation. We said earlier, but here I am writing down so that you could understand that what is the difference between the strength, stiffness and hardness. These three are different, and these three definitions are put together here so that you could understand. Once again, the hardness is a measure of material's resistance to surface deformation. Okay. For some metals like steel, hardness and tensile strength are roughly proportional. All right. So, there are American Society of the Steel, and there they have the tables. You can find out that how much, what is the actual values. So, this is the difference between strength, stiffness and hardness. The definitions are noted down here. Mechanical properties in design and manufacturing. Mechanical properties determine a material's behavior when subjected to mechanical stresses. All right. Now, properties include elastic modulus, ductility, hardness and various measures of strength. Now, here the dilemma becomes that mechanical properties desirable to the designer such as strength usually make manufacturing more difficult. What we mean to say is that there is a concept of machinability. I just told you earlier, machinability is ease of machining. Now, when you are designing a part, you are also selecting the material, all right. Now, if the material has poor machinability, it is difficult to machine. For the designer, it is easy to select that material because he needs particular properties for that and so on. But for the manufacturer, it is very difficult to machine that particular part. So, the designer, for example, can actually have a substitute, if it is possible at all, of that material. Okay. Instead of selecting the low machinability material, he can actually select a substitute which will have reasonably good machinability, so that it could be easier for the manufacturer to produce that part. So, this is the concept which we keep on telling as the design for manufacturability. That means, you have to design in such a way that the part can be manufactured in a proper way, it can be manufactured easily. For example, there are certain components, there are certain features in the design that are kept by the designer, okay, but those features are extremely difficult to manufacture. Now, it is up to the designers to substitute, to change those features in the design, so that it could be manufactured properly, and that can be done, that if the designer, in many times the designer can do that. So, then we say that designer is improving the manufacturability, and design should always be for manufacturability, because ultimately design will not remain on the paper, design will be manufactured. Okay. If you are designing a part, that part has to be manufactured. So, you have to always understand that whatever you are designing, it should be easy for manufacturing. Okay. There should not be any conflicting feature in the drawings, there should not be any conflicting features in the design parameters. Okay. So, that is the dilemma, that mechanical property is desirable for the designer. So, high strength, for example, that is very difficult to manufacture, as I said. The manufacturing engineer should appreciate the design viewpoint, and the designer should be aware of the manufacturing viewpoint similarly. So, this is in both way, as I was telling you, the design for manufacturability as well as the manufacturer should understand the designers as well. Stress strain relationships. Okay. Three types of static stresses to which materials can be subjected. Many of you might be knowing that these are the tensile stress, tend to stretch the material, okay. Compressive stress tends to squeeze it, okay, and the shear. So, overall what you can say is that in one word, that this is the tensile, okay, when this force is applied here. Now, when the force is trying to compress, all right, this will create the compressive stress, all right, and if it is shearing, force is like this. So, this is the third case, shear. This is the first case, this is the second case. These are the forces acting. Let us say these are the forces, okay, and this is, you can say, the shear stress or the shear force, all right. Now, shear tend to cause adjacent portions of materials to slide against each other, all right. It means that what it will have is, it will elongate if the forces are like that. If the forces are applied like that, it will be squeezed, all right. If the forces are like this, so the part will then be like this, it will be adjacent portions, these portions try to slide against each other. So, this is the result. Stress strain curve basic relationship is the basic relationship that describes mechanical properties for all these three types. Okay, what are the mechanical properties when it is a tensile stress, or it is a compressive stress, or it is the shear stress. Okay. So, let us see this. Engineering stress defined as force divided by original area. Okay, this is the engineering stress. Now, here in this case, of course, this is the engineering stress which is measured in the megapascal. Okay. This is the force applied measured in the unit of Newton, and the original area of the test specimen, this is given in the millimeter square. So, force upon area, but in this case in engineering stress, this is the force applied by the original area of the test specimen. We will come in the next some discussions, I mean after some time, that what is the difference between engineering stress and different other stress, the concepts are also there. So, how they are different, I will come to that discussion later. Engineering strain therefore, defined at any point in the test as this L minus L 0 divided by L 0. L 0 is the original gauge length, okay. And after the elongation, the L 0 has become L, it has been elongated. Suppose there is the material when it is being elongated, all right, it is given this and it is elongated like this. So, this is small, this is L 0 and this is the L, okay, after being elongated. So, this is the engineering strain, and engineering strain is millimeter by millimeter. So, therefore, it is dimensionless, because L minus L 0 is in millimeter divided by the original gauge length, which is also in millimeter. Okay. So, once again this is the original length, this is the length after the elongation, and the engineering strain is given by the difference between them L minus L 0 divided by the L 0, which is the initial gauge length. Okay. If you see this here, this is the stress strain curve. Okay. This is a very popular stress strain curve, you must have seen, you must have studied that in some of your courses. So, particularly this is the stress strain curve for a material which is not brittle material, by the way, because brittle material stress strain curve obviously will be different, I have told you earlier. So, this is for the ductile material, all right. Now, in this here we have the stress, and along the x axis we have the strain, all right. Now, the stress is given in here, of course, it is in the American system, from American book it is written. So, it is given in pound by inch square. So, normally we take as the kilogram per, I mean in our unit which we use, kilogram per centimeter square or Newton per meter square, and so on. Strain here, as I said, that strain is the dimensionless, because it is millimeter by millimeter. Okay. So, here as the strain is applied, the stress increases proportionally, all right. So, when the normal, this is the let us say friction force and this is the normal force. So, when the normal force is applied, the friction force increases. So, this concept similarly, when the strain is increasing, the stress increases proportionally, and it increases to proportionally to a certain level, okay, which we call as the elastic region, as it is, as you know probably. And then after that elastic region, the yielding starts, all right, and then after that the material no more remains in the elastic state and the plastic deformation starts. So, here what happens is that in this elastic region, see, after that yielding starts, there is about 0.2% of offset between these points, okay. From here and this actual curve, this is the offset which is about 0.2%. Then it goes to the plastic state from the elastic. Then of course, it will be curve will be like this. The entire thing is the plastic region. It will indicate the maximum load, and sometimes after that the stress strain curve goes in this way and it fractures. So, how to define the yield point here? Yield point y. The yield point y, as it is written here, as you can see from this slide, is typically defined as the stress at which, this is the stress at which a strain offset of 0.2% from the straight line has occurred. All right. So, this is the exact identification of the yield point, that it has to be 0.2% offset from this straight line, that is in the elastic region, and that will actually define where is the yield point. And as I said, that after the yield point it goes in a nonlinear way, and maximum load occurs, all right, in the plastic region. Then the necking occurs and it becomes unstable, and at any point after the maximum load the fracture occurs. Fracture is basically the segregation of the material from the body. So, this is important to understand in case of machining particularly, because in machining we actually segregate the excess material from the workpiece, from the job, okay, blank, and that excess material to be segregated as per this principle, in case that material is of course ductile material. In case of brittle material, it breaks in here, all right, it does not go to the yield point, okay, because it is a brittle material like cast iron for example. Okay. Elastic region in stress strain curve, that the relationship between stress and strain is linear. This is, I mean to say, what happens in the elastic region. Okay, properties. First property is the relationship between the stress and strain is linear, as you can see that this is linearly going from this point 0 point as we are straining. So, the stress goes proportional to the strain. Second property is that the material returns to its original length when stress is removed. Okay. So, material is deformed certainly, and that deformation may come back to the initial position, will come back to the initial position here in case the strain is removed. Okay. These are the properties in the elastic region. The stress strain relationship in the elastic region is defined by the Hooke's law, as many of you might be knowing that. So, this is, since the stress is proportional to E, that is the strain. So, the stress is equal to constant into E, and this constant, as you understand, that this is the slope which of this line, and this is called the modulus of elasticity, and this slope is measured in a megapascal unit. Okay. E, Young's modulus, is a measure of the inherent stiffness of a material. Okay. So, this is indicative of the inherent stiffness of the material. Its value differs for different materials, of course, like mild steel will have something, alloy steel will have something else, okay, and so on. So, that depends on the material stiffness particularly. Yield point next here, as I said, once again I will repeat that when it is 0.2% offset from the straight line, as stress increases, a point in the linear relationship is finally reached. In this linear relationship, a point finally reaches when the material begins to yield. Okay. Yield point y can be identified by the change in the slope. See, since this is going in the other way, the slope does not remain the same as in case of the elastic region, all right, and the slope changes. So, therefore, the yield point can be identified by the change in the slope at the upper end of the linear region. So, at this the slope will be different than in here, all right. Why? That yield point is a strength property, okay, meaning that yield point varies, the location of the yield point varies between the materials of different strength particularly. Other names of yield point is yield strength, it is also called, yield stress also it is called, or elastic limit, meaning that up to that point the elastic limit, it is a material is still elastic actually. After this point the material deformation begins in a as a plastic deformation. Okay. So, therefore, that yield point is also called as the yield strength of the material, because this is, as I said, that this is the strength property, yield point is the strength property of the material, and different materials with different strength will have the different yield point, location of the yield point, all right. This we have to understand, and also it is called the yield stress or the elastic limit. Okay. Now, in the plastic region what happens, that this is the plastic region in the stress strain curve, yield point marks the beginning of the plastic region, because this is the point, below this is the elastic deformation and beyond this point is the plastic deformation. So, therefore, this is the yield point is the beginning of the plastic deformation, okay, or the end of the elastic deformation, all right. The stress strain relationship is then no longer guided by the Hooke's law, because in the Hooke's law, which is applied in this region, here the stress is proportional to strain and it is a straight line. Okay. So, therefore, the Hooke's law, which says the stress is equal to the Young's modulus and the strain, that no more remains valid in this region, in the plastic region. As load is increased beyond y, beyond this yield point, elongation proceeds at a much faster rate. As you can see that it goes non-linear and it goes at a faster rate than before, causing, because you can see that for example, here from here it goes very rapidly, the strain happens very rapidly. Okay. At a, then causing the slope of the curve to change dramatically. So, here at each point you can see that the slope of the curve is changing, all right. Here it was constant, stress was constant, or stress by strain was constant, stress was proportional to strain, and in this region it does not remain that way, that is, stress is not any more proportional to strain in the plastic region. Tensile strength in the stress strain curve, elongation is accompanied by a uniform reduction in the cross sectional area, all right, consistent with maintaining the constant volume, because volume has to be constant. So, therefore, in the cross sectional area there is an uniform reduction as the elongation happens in the plastic region. Okay. Finally, the applied load F reaches a maximum value. This is the maximum value of the load that is being applied, okay. And engineering stress at this point is called the tensile strength. At this point, whatever will be the engineering stress, this is the tensile stress, all right, tensile strength or ultimate tensile strength of the material. So, therefore, the tensile strength will be defined by the maximum of this force that is applied divided by the A0, and A0 remains like in case we have seen here earlier, this is the original area of the test specimen, okay, because we are defining the engineering stress, all right. So, the ultimate tensile strength or the tensile strength in short as it is called, this is the maximum force that has been applied that after the tensile, after the yield point divided by the original cross sectional area, all right. Here you can see these are the tables, thus for your understanding that these are the elastic modulus, okay, that value E that we said, that is also called the elastic modulus or the modulus of elasticity. Okay. For example, you can compare, okay, the modulus of elasticity of aluminum and alloys, all right. This is in megapascal. Cast iron is more, as you can see that, all right. Now, in comparison to cast iron, copper and alloys have less modulus of elasticity, but it is still more than the aluminum and the alloys, as you can see here. Now, the iron has much more than all of them, and so on. The lead is a very soft material. So, here the modulus of elasticity is very low, all right, probably the lowest in this table of metals, whereas the tungsten, as I was telling during the discussion, during our discussion about the material, that it is a very hard material. So, therefore, the modulus of elasticity here is the maximum, which is 407 into 10 to the power 3 megapascal. All right. Now, for ceramics and polymers, if you compare, the diamond of course will have the maximum, because it is the hardest material. It can scratch the brittle and the hard material like glass, for example. All right. And next to that is the tungsten carbide. Here you can see the tungsten has the 407, and when it is in the form of the carbide, tungsten carbide, it becomes even more. This is 552. Whereas, the lowest one in this table will be the polyethylene, here which is a very low density, and the modulus of elasticity is only 0.2 into 10 to the power 3 megapascal, and you can find out. So, this is for your understanding that where the materials stand in terms of the modulus of elasticity, hardness also. Okay. Then you can see, you can compare the materials from the point of view of the modulus of elasticity. Similarly, the yield strength, you can also compare. This is another table which shows the yield strength and tensile strength for the selected metals. Here is the yield strength, which is the megapascal in megapascal, and tensile strength in megapascal. You can compare aluminum, annealed aluminum, okay, aluminum, then the aluminum alloys, cast iron, copper annealed, copper alloys, okay, magnesium alloys, and so on. And here you can see the megapascal wise what will be the yield strength. So, while calculating, while designing the part, while calculating the different kind of parameters, design parameters, these tables are very useful, because you have to know when you are using a particular material, you have to know what is the modulus of elasticity of that particular material, or what is the yield strength of that particular material. Here in this table you can find out the yield strength of the nickel, steel, okay, stainless steel for example, and then titanium alloy. So, always you can see that the titanium alloy, as I was telling about the titanium here somewhere. So, this has the maximum yield strength. Okay, this is the so, therefore, the strength wise these are the alloys which sort of very good in the very high, having very high value in the table of the yield strength, okay. And tensile strength as well. You can see the tensile strength is also probably the maximum in this table, yes, all right, among all these materials. So, this is almost in the increasing order of the yield strength and the tensile strength, almost, not always of course. Well, let us see what is ductility in the tensile test. Ductility, as we said, that this is the ability of a material to plastically strain without fracture. This I have told already here earlier. Now, therefore, the elongation that is taken in percentage, okay, normally. How much it will be elongated, that depends on the specimen length at fracture. So, when it is fracturing, what is the specimen length, okay, that exactly is taken. Then the original specimen deducted from this, from the LF, that divided by the original specimen length in millimeter, that gives you the elongation in the percentage, okay, that of course multiplied by 100. LF is measured as the distance between the gauge marks after two pieces of specimen are put back together. Now, what we mean to say is that LF, how you measure it? It has already broken, all right. So, we are saying that this is the specimen length just at fracture. So, normally during the testing what happens is that it is broken, that piece specimen is broken, then as soon as it breaks. So, therefore, after that those two pieces are joined together and the length is measured. So, that length will be the LF, okay, that is the elongation in percent, specimen length at fracture. Now, here you can see the ductility of various engineering materials. Again, this table I have mentioned just for you to understand that what are the typical values. Okay. The ductility is given as the percentage of elongation, these are the typical values. Now, you can see that aluminum alloys, cast iron, copper, okay, magnesium, nickel, annealed, metals containing steel, low carbon, high carbon, alloy steel and so on, and you can see that elongation. All right. For example, here if you see the cast iron, as I was telling that the cast iron cannot be elongated because it is the brittle material. So, therefore, here you can see that the cast iron is very less, it is 0.6%. Okay. And similarly, the ceramics for example, here it is given as a 0. All right. So, it just cannot be elongated, it will break because they are very brittle materials. So, therefore, although the ceramics, as I said earlier, that this material is used for making the cutting tool, okay, because these ceramics can withstand very high, these are of very high strength, they are strong, and they can also withstand high temperature. So, therefore, they are used as the tool material. But however, these materials, as you can see that elongation become being 0%, that means they cannot withstand any shock or any fluctuation in the force. Okay. So, therefore, one has to be careful in case there is a fluctuation in the forces or there is a shock in the during the process, then the ceramic tools may not survive well. All right. For example, thermoplastic polymers, they can be stretched, okay, and here it is elongation is 100%, okay, and so on. So, you can have a fairly good idea about the materials in terms of their elongation, that which material is so to say ductile, which material is brittle and so on, and how much brittleness is there, how much ductility is there, that depends on what is the percentage of elongation one or the other material has. Well, here next is the true stress, and the stress value obtained by dividing the instantaneous area into the applied load. Okay. So, you can find out the difference between the true stress and the engineering stress, because this A was that earlier for the engineering stress it was A0. So, that was the initial area, okay, cross section area, but A is the actual instantaneous area resisting the load, that area, particularly that area which is resisting the load. So, that area has to be taken care of in the case of true stress. All right. So, therefore, it is called the true stress, because in engineering stress it is taken as the initial area. So, that area is not the actual area which resists the load, and A is taken in millimeter square, F is the force which is applied, and the true stress here, this is F by A, this is taken as in case of engineering stress, this is taken in the megapascal. Okay. Similarly, the true strain differs from the engineering strain in the way that the true strain provides a more realistic assessment of the instantaneous elongation. Similar to the true stress, that this is the instantaneous area resisting the load, here also the we have to assess the instantaneous elongation per unit length, then the true strain has to be used, not the engineering strain. So, true strain is given in this way, that dL divided by L integrated from the L0 to capital L0 to capital L, which is equal to logarithm of the L divided by L0. So, logarithmic, why it is taken? Because logarithmic strains, okay, they are additive in the sequential processes. So, this is the advantage why the true strain is expressed in the logarithmic scale. All right. This is not true in the linear strain. In linear strain, it is not additive in the sequential process. For example, a bar is strained from, let us say, L0 to L1. Okay. This is capital N1, let us say, or let us say this is small L0, because afterwards we have taken all of them are small L0. So, take it as a small L0 to L1, then the true strain is equal to, as per using this formula, this will be logarithmic of L1 divided by small l0. Okay. This will be small l0. If the bar after the being elongated by up to L1, if the bar is further extended to L2, for example, from L1 to L2, then the strain or the true strain will be, let us say this is E2, this will be logarithmic of L2 by L1, which was earlier. All right. Now, the total strain will be this E1, all right, E1 plus E2, and this will be equal to log of L1 by L0 plus log of L2 by L1, which is ultimately log of L2 by L0. So, what you can see is it is easy, whatever stages you have of the elongation, what matters is the final length and the initial length, okay, L0, and that you take the ratio of that and logarithmic of that value, logarithmic of that value will be equal to the total strain. So, while estimating the total strain, it is just the additive, okay, in the sequential process. That is what we said, that logarithmic strains are additive in the sequential processes. All right. If previous engineering stress strain curve were plotted using the true strain, true stress and the strain values, let us say now we are putting the true stress here, all right, and true strain here. In the elastic region in here, there is almost no change, all right, because this is the elastic deformation. Here the strain values are small and true strain is nearly equal to the engineering stress, because the small strain values, all right. The reason is that the cross sectional area of the test specimen is not significantly reduced in the elastic region, all right. Therefore, of course, engineering stress and true strain will be the same, because it is either the initial length or it is the final length. There is not much of a difference between them. Okay. Now, here it is, therefore, yield point start of the plastic region, and up to that point engineering stress strain curve and the true stress strain curve, not much of a difference between them. All right. Now, difference between true stress strain and the engineering curve, to look at this further. Okay. In engineering counterpart, in the plastic region it lies actually, basic difference. So, we have seen that in the elastic region there is not much of a difference, because the elongation does not happen very much. Okay. The stress values are higher in the plastic region. Stress values are higher in that is why the deformation has changed from the elastic to the plastic, all right. Because the instantaneous cross sectional area of the specimen, which has been continuously reduced during the elongation, is now used in the computation. Okay. This is the reason why the stress values are higher in the plastic region also, because the instantaneous cross sectional area of the specimen that has been continuously reduced, this is being used in the computation. So, as strain becomes significant in the plastic region, the values of true strain and engineering strain then therefore diverge. True strain can be related to the corresponding engineering strain by this formula, that is this true strain is equal to log of the 1 plus engineering strain. Okay. Now, similarly, true stress and engineering stress can be related to this expression. So, this is the true stress, and this is equal to the engineering stress into 1 plus E. Okay. This you can see that this is the difference. So, this is the strain that we have taken, okay, that was the engineering strain, all right. This small e is the engineering strain, this is the true strain, all right. So, in case of stress, it will be true stress is equal to engineering stress into 1 plus engineering strain, all right. Strain hardening in stress strain curve, this is another phenomena which happens in the plastic region after the region crosses the yield point. Note that true stress increases continuously, okay, in the plastic region until the necking. in the engineering stress strain curve, the significance of this was lost because stress was based on the incorrect area value. You understand what I said? Meaning that when we are finding out the stress in the case of the engineering stress, then the area we have taken as the initial area. So, it has nothing to do with the area that is instantaneous. So, therefore, in the engineering stress strain curve, once again the significance of this, that the true stress increases continuously in the plastic region, it was lost. All right. What it means is that the metal is becoming stronger as the strain increases. All right. This is something which has to be understood, that metal is becoming stronger as strain increases because of this, that we are taking the instantaneous area and not as in the case of the engineering stress or engineering strain. This is the property called the strain hardening. So, if we have to define, the definition of the strain hardening will be that this is the material being able to withstand the increased load despite the uniform reduction in the cross sectional area. And this is the phenomena which is called the strain hardening, which happens in the case of the plastic region after the yield point. All right. When the plastic region of the true stress strain curve is plotted on a log scale, okay, here it is the true stress in the log scale and here it is the true strain in the log scale, it becomes a linear, of course, understand that. So, this is the necking, all right, up till that it is the linear, and afterwards it will be fracture and it behaves in a very different way and in a very erratic way. In fact, it does not follow a certain rule. All right. Now, let us see what is flow curve. All right. Because it is a straight line in a log plot, I mean this one. All right. The relationship between the true stress and true strain in the plastic region. So, mind it that this is the plastic region, all right, because here what we are having is the up till the necking. Okay. In the plastic region can be expressed as this, that this is the true stress, all right, and this is the true strain. This is true stress is equal to true stress equal to some constant k into the true strain to the power small n. Now, that small n, this is actually the strain hardening exponent. Okay. This is called the strain hardening exponent, and this k is a strength coefficient in megapascal. So, this is actually a constant because this is proportional to e to the power n, all right, strength to the power n. So, this is the strength coefficient and this is taken in the megapascal to make the unit of the left side and the right side the same. K equals the value, the significance of the K is the value of true stress at a true strain value equal to 1. Okay. So, if you see that this is 1 to the power n. So, this sigma will be equal to K, all right. That is what we are saying, that the K equals to the value of true stress, all right, at a true strain value equal to 1. Okay. This is equal to the value of the true stress. As you understood that this factor becomes 1. So, stress is equal to K, that is what it is being said. So, this is called the flow curve, where the true stress is defined in terms of the true strain, all right, and for that we have the factor which is called the strain hardening. And once again the strain hardening is the ability of the material to withstand the increased load despite the uniform reduction in the cross sectional area. See, mind it, this does not happen before the unstable K point. So, not happens immediately at the yield point. Okay. It starts happening when it goes to maximum, and there the load becomes maximum, and there the necking starts, and that is the point, I mean that is the situation when the that we are calling that uniform, despite the uniform reduction, okay, it can withstand, the material can withstand the increased load, and this ability of the material is the or the property of the material, it is the strain hardening factor is used here to express the relationship between the true stress and the true strain through a coefficient which is called the strength coefficient. So, this defines the strength of the material, this is the strength coefficient. Rest of the things we will discuss in our next discussion session. Thank you very much for your attention.